All right, so we're considering the paper, which is a Diploma in Automotive and Heavy Equipment. This was written in April 2025. And this is revision, which means we'll just go straight to the package. We'll not take too much time looking at the basics, which we've already covered. All right, right away, let's pick up question number 1. So it says, in relation to hydrostatic forces, define the following. Number 1, center of pressure. Center of pressure, when you hear the word center of pressure, under this, when we're dealing with hydrostatic forces experienced by a body that has been immersed in a liquid, we're talking about that point where that hydrostatic force is acting. The hydrostatic force on a body immersed in that liquid, where it is acting, that is the center of pressure. Then what we call total pressure is basically the total hydrostatic force that an immersed body experiences due to the weight of the liquid on the surface or above that surface which has been immersed. Pascal's law states that the pressure in a fluid at rest is evenly distributed in all directions. So question number 1C says, the figure below shows, let me just remove this. Okay. Yeah. The figure below shows the circular opening in the cylinder in the inclined wall of a reservoir, closed by a disc valve, 0.9 meter diameter. The disc is hinged at H, and the balance weight W is just sufficient to hold the valve closed when the reservoir is empty. Calculate the additional weight that should be placed on the arm 1.2 meters from the hinge in order to keep the valve closed until the water level is 0.7 meters, 0.72 meters above the center of the valve. So this is our arrangement. This is the weight to be put there. We have a hinge and the supporting lever. The length there is 1.2 meters. This whole gate, we're told the diameter is 0.9. Rather diameter 0.9. So which one is our gate? It's here, the disc valve, the valve there. So meaning from there to there, that is 0.9 meters. That is also 0.7 from the free surface coming to the center of gravity of the body, which shows that this is already our X bar. Now with that, let's try to get around with the data. First thing we have is the diameter. Like we said, the diameter of the disc, the valve is 0.9 meter. The area, so given the diameter, we can now compute the area, which is pi d squared over 4. Pi times 0.9 squared divided by 4, giving us 0.6362. Then the angle of inclination is 60 degrees. We already said that the distance from the free surface to the center of gravity of the whole body, the whole arrangement there, is 0.72. Specific weight, we're dealing with water, meaning that the specific weight remains 9810 newtons per cubic meter. Then I, the moment of inertia, second moment of area about the center of gravity, is normally pi d4 over 64. So pi times 0.9 raised to power 4 over 64. When you enter this in your calculator, you're supposed to get 0.03221. Now let's get back to the working. First things first, let's find the pressure force acting, that hydrostatic pressure, where the pressure due to the weight of the liquid on that plate, that's the one we call P. The formula is here, omega A x bar. Specific weight is 9,810 times our area, which is 0.6362, times x bar, this one, 0.72. So this sum of computation gives 4,493.608. Then we also need h bar. You can ignore whatever is coming the other end. In fact, let me just remove it now because this could be giving us wrong information. This is h bar, the depth of the center of pressure from the free surface to where we are. Because this is at an angle, and of course the angle was already given, we can right away just put it on the left so that we don't have to struggle. So we already have been given the angle. The angle is actually 60 degrees. So we just plant it there that our h bar is Ig sine squared theta times a times by x plus same by x. So we can do the substitution. Ig, we already found it to be 0.03221 times sine squared 60 over our area 0.6362 times x bar, which is 0.72. Whatever is going to come from here, whatever is going to come from all this, you add to 0.72. Therefore, our answer comes out as h bar is equal to 0.773 meters. So this is the distance from your free surface up to where P is acting, there. Now, we also need now to find what is the distance from P, where P is acting, and where G is. Just this distance, that vertical distance. We subtract. This distance from the free surface to there, this is 0.773. So we have to subtract this 0.72. That is how come we can get that difference there. So 0.773 minus 0.72. Our answer is 0.053 meters. 0.053 meters. We'll leave it there. We'll come back to it. Now let's take moments about H here, since we have all the tools now. As per custom, summation of clockwise moments would be equal to the summation of anti-clockwise moments. So you can see that P multiplied by the distance from P to H. Now you can see that from H to G, the distance is 0.6. But what is missing? Let me grab a quick writer, just a pen. We already have the vertical distance, but what is missing is this distance now from there to there. Now that we already have the vertical distance, which is that, so in other words, what we are having now is that we have this distance, which we don't know, and yet we already have the vertical distance, which we already calculated when we subtracted. It already gives us a right angle triangle. So what happens here is that this side we have, we have been given this one, and yet we're looking for this, the hypotenuse. In fact, let me not even use H, let me use something else. That's why I may decide to put maybe just a K. Yeah. So the angle in this case, in this corner here, is actually 60 degrees, this same one here. So what do we do now? The ratio between this and this hypotenuse, because this is opposite, is sine. So when you say y over k, you get sine theta. Supposed to be equal to sine theta. Now the secret is this. Our target, let me just put there. In fact, you can even say sine 60 because that's the actual angle given there. So we're looking for k. To find k, we're therefore going to say it's supposed to be y over sine 60. Meanwhile, y is this number we have here, which is 0.053 divided by sine 60. So to get the full perpendicular distance, we have to add this 0.6 to what we have just found here, which is this ratio here. So this completes the perpendicular distance that we are trying to get here. And let me just remove here. Then okay, all right. So deal with it. So with that in mind, you can just the thing first. Yeah. Right. So what happens now is that we are now going to say this is 1. This times that perpendicular distance from there all the way to there, giving us 0.6 plus what is coming from there, then equals W times this perpendicular distance, 1.2. All these we've already calculated for P up here. And that P was 4493.608 newtons. Then with that, we now say, let's, we just substitute where it is there so that the only unknown will be this W. So 4493.608 times, this is what you have from there, 0.6612 equals W times 1.2. So making W the subject, you notice that that additional weight we're looking for, that W, is actually 2475.975. Moving on, question number 2. Define the following compressible flow. So this is the type of flow, fluid flow where the density of the fluid changes significantly due to the changes in pressure and temperature. That's where the compressibility comes in. Then there's also incompressible, the opposite of that, case where the flow and density of the fluid, they remain stubborn, they remain constant. They cannot be compressed or expanded, so they can't be changed. So practically not possible to even compress such a liquid or such a substance. Then B, state the conservation of mass principle in fluid flow. So in fluid flow, the mass flow rate of a fluid remains constant through a flow system unless there's some leakage or some addition of mass or some masses. Now comes the next question. Says we have a pipe 200 meters long slopes down at 1 in 100 and tapers from 600 millimeters in diameter at the higher end and 300 millimeters diameter at the lower end, and carries 6,000 liters per minute of oil of specific gravity 0.8. If the pressure gauge at the higher end reads 60 kilopascals and neglecting losses, determine. Okay, move that. Determine, first of all, the velocities at the two ends, pressure at the lower end. So let's pick out information given. Number one, the diameter, the area one, because there are two areas. The first area is this one, 600 millimeters. So what we do with the 600 millimeters, we convert it to meters. When you divide 600 by 1,000, you get this number we've put here, 0.6. So pi times 0.6 squared divided by 4. The answer is here, 0.2827. Then area 2, that is pi times 0.3 squared over 4. The answer we get is 0.07069. That's area 2. Again, we ensure that these are maintained in square meters. The discharge is in liters per minute. So to convert liters to cubic meters, that's why we've divided by 1,000. To convert those minutes per minute to seconds, this is where the 60 is coming in, because every minute has 60 seconds. Then this one, at the higher end where the diameter is big, this is where we have the data, the Z2 as 2 meters. The lower end, to get this height, we measured from the lower end going up, meaning that this one we're going to call Z2 is actually our reference point. Therefore, it's 0. Then the other one, which is Z1, the one on top, Z number 1, it's exactly what we have here. Z1 is the same one we have here, which is 2 meters. Now, how do we get the 2 meters? We've been told that the length of the pipe is 200 meters. The slope is 1 in 100. So whenever you see this slope, just multiply by the length, then you're good to go. Slope is 1 over 100. So that's why we have 200 times the slope. Then we end up with the actual height. Specific weight. We have been given that the specific gravity is 0.8. So to get the specific weight, we invite specific weight of pure water, which is 9810, and we multiplied by that one, the 0.8. So 0.8 multiplied by 9810, we end up with 7848 newtons per cubic meter. When you go back in the question again, you find yet another parameter which says the pressure gauge at the higher end reads this. The higher end here, this is our section 1. The lower end here, this is our section 2. So that's why we're saying that pressure 1, therefore, is 60,000 pascals, because kilo is now taken care of. We started the velocities at the two ends. We invite the formula for the discharge, which is discharge is equal to AV, area 1, velocity 1, which is equal to area 2, velocity 2, and it goes on and on, because this is that conservation of mass principle we're talking about, ending up saying that the discharge remains constant. So meaning that you can equate Q to this or Q to the second set, or you can even equate these products on their own. A1, V1 is equal to A2, V2. The result is the same because the analysis is coming from such an environment. Next, oh, sorry, let me just remove those. It works. Okay, it does. Okay, it's fine. So, okay. And then, all right, seems no problem. So, the next one is now where we just do the substitution. This charge is 0.1 is equal to area 1, which is 0.287227 times velocity 1. Then making V1 the subject from there. Sorry, we went to the wrong side. When we make V1 the subject, you end up with 0.3537. To find V2, we repeat the same process. Q is equal to A2 V2. So Q, the discharge is 0.1. This is equal to A2, which is 0.07069 times velocity 2. So when you make velocity 2 the subject, your answer is 1.415 meters per second. Let's now calculate the pressure at the lower end, which is like P1, rather P2. For this one, we have to invite Bernoulli's equation. So Z1 plus P1 over omega plus V1 squared over 2G is equal to Z2 plus P2 over omega plus V2 squared over 2G. We do the substitution. Here we said that Z1 is 2 plus pressure 1 is also 60,000 divided by omega, which is 7848, plus V1, which is 0.3537 squared over 2 times 9.81. This is equal to, for Z2, it's 0, plus P2, we don't know what it is, so we leave it, divided by 7848, plus V2 is 1.415, so square it, divide by 2 times 9.81. So from all that, our answer comes out as 74,945.15 pascals. And you can already see that we've just found the final answer, maintaining the unit in the same pascals. Question number 3. Reynolds number is defined as the ratio of the inertial force to the viscous force. Show that the Reynolds number for a given fluid mass density that rho and dynamic viscosity mu flowing at the velocity u through a pipe of length L is given by Reynolds number is equal to that. So here, I think, let me just correct it. Where this view is supposed to put you, I think I just found them annoying because here, you and mu, they're almost looking like inseparable twins. Okay, so having done that, we come here now. Reynolds number, the definition of Reynolds number according to the question is the inertial force over viscous force. Now what do we do with the two numbers? Since we have these, all we need is to put the formula for this, put the formula for that, and simplify. So inertial force, that's Fi, is equal to density times U squared L squared. Then the viscous force, that's Fv, is mu U L. So with these are the ones that we're supposed to come and substitute. So after substituting, what are we getting? We have Reynolds number is equal to Fi over Fv. And then our Fi is this expression that we had. Just a minute. Okay, good. Fi is Z, density U squared L squared. Fv is mu U L. So that combination already gives us these L will cancel with this L so that you just remain with 1. Then U, there's U squared and this is just U. It's 1 into U squared, you remain with one of them there. Meaning that on top you have density UL over the one which is intact, which is mu. So that, after that, you can even write hence proved. Let's go to the next one. Again, this is now actually question B. Let's get some quick. This one. The question says a 6-meter long pipe inclined at an angle of 20 degrees to the horizontal. The smaller section of the pipe is at the lower end is Z, 100 millimeters in diameter, and the larger section is of the pipe is 200 millimeters in diameter. The pipe is uniformly tapering and the velocity of the water at the smaller end is Z, 1.8 meters per second, assuming the datum line passes through the center of the pipe at the lower section. Determine the pressure difference between the sections of the pipe. So as per tradition, first thing we have to do is to start organizing data. Start organizing data so we can make sense out of it. Okay, where is our data? Yes, so the first thing we have is that the length of the pipe is actually 6 meters. And this one has made our work easier. In the previous question, we were given the length of the pipe, but when it came to the angle, all we had was just what's this? All we had, instead of the angle, was the slope, making it a bit tricky. So length 6 meters, Z1 this time around the lower end is 0. Then next, Z2. To find Z2, we just make almost like a right angle triangle, dropping down from there, coming there. And this is the Z2 we're looking at. Along the length here, this is 6 meters. You can already see that this Z2 we're looking for is basically opposite this angle, leaving us with sine. So meaning that 6, rather Z2 over 6 meters gives us sine 20. So when you make Z2 the subject, you end up with 6 sine 20, which gives birth to 2.052. Area 1. Our first area, which is area 1, is pi times 0.1 squared over 4, which is giving us 0.007854. Then moving on, area number 2, we're just going to use the same formula, but to change on the diameter side, we say pi times 0.3 squared over 4. Our answer is 0.07069 square meters. Velocity 1 at the lower end, at the smaller section, 1.8 meters. Specific weight. Now, here there is no mention of specific weight anyway, it's silent. Then where is this number coming from? Because it hasn't been given, then where has this come from? When you check the question carefully, it says the velocity of water. So there's a mention of water, and water is that standard fluid which has a density of 1,000 kg per cubic meter, as well as specific weight 9,810. So there we're covered. The moment they mention water, that's where we are. We can now invite discharge formula. So A1 V1 is equal to A2 V2. You make V2 the subject, you have A1 V1 over A2 being equal to our area 1.007854 times velocity 1, which is 1.8, divided by area 2, which is 0.07069. From that computation, that's how come we have this 0.2 meters per second. That is our second velocity. A very low one at that, but that's what we have to work with. Next, we invite Bernoulli's equation so that we can find the pressure missing there. So Z1 plus P1 over omega plus V1 squared over 2G is equal to Z2 plus P2 over omega plus V2 squared over 2G. Now, here we gather P1 minus P2 over omega, which is equal to everything else going to the other side. We have Z2 minus Z1 plus V1 squared over 2G minus V1 squared over 2G. This one was V2, the other one V1. Then you can cross multiply. Our target is the pressure difference, which is P1 minus P2. So you just cross multiply by this so that we get rid of it. Multiply it on the other end. So there it sits now. So omega Z2 minus Z1 plus V2 squared minus V1 squared over 2G. All right. So we have done that. The next thing we can do now is P1 minus P2. We do the substitution. Specific weight is 9810 times open bracket Z2 is 2.052 minus Z1, that's the data, it's 0. Then plus V2 squared is 0.2 squared minus V1, which is 1.8 also squared, divided by 2 by 9.81. Okay, just a minute. Okay, there we are. Next, good. So question number 4. Distinguish between gauge pressure and absolute pressure. So, when we talk about gauge pressure, this is the kind of pressure you measure when you use the atmospheric pressure as our zero, as our reference pressure. But of course, in practice, there are cases where we cannot afford to do that. Then absolute pressure. This is the pressure measured above a perfect vacuum, the absolute zero. In other words, the moment you add gauge pressure and atmospheric pressure, then you end up arriving at gauge pressure plus atmospheric pressure, then you found the absolute pressure. Question number C, the other one was B, says we have a single column manometer used to a pipe is connected to a pipe containing a liquid of specific weight 0.8 as shown in figure Q4 below. The ratio of the cross-section area of the reservoir to the cross-section area of the right limb is 100. Okay, so from there we say, let's invite the data. Of course, that's the diagram we're going to use. First thing is specific weight for the liquid that we have available. So now in our working, we start first of all by applying Pascal's law. So here we're saying that ratio of the area, small area over big area, times H1. Then multiplied by open brackets, the difference between the densities of the specific weights, which is the one for mercury and the other one, which is W. So A over A times H1, and then the other one on the other end is W1 H1 minus WH. When you do the substitution, you find that A, small a is 1, big A is 100, then H1 is 0.5. Then we proceed to say omega 1, which is 133,416 minus 7848. Then plus, open brackets. This time around, we come to the other one, the other part as well, where we use Y. So the specific weight of the manometer liquid, which is mercury, times multiplied by 0.5. Take away 7848 times again 0.3. So with the substitution, we have 133,416 minus all that. And the result, let me get to there. Yes, the result is 64,981.44.